Okay, so welcome back. Even though I haven't gone away to actually record that yet, I will cut and splice, and this might all make sense by the time we get down to the end. Might have different clothes when I come back next time. So, wow, why are you so wrapped around this whole Reynolds number issue? Well, I think it's indicative of what's causing the problem on my wing. It's not that low Reynolds number causes a problem. The low Reynolds number just tells us something about the flow conditions that are causing the problem. So it's a measure that we can look at. It's a non-dimensional measure we can look at to say, oh, am I in a problem region? Am I in a good region? Because physically we can't see the flow on the wing. If you have very controlled conditions and a smoke flow injector and all that, you might be able to see the boundary layer. Very specialized equipment, you can measure the boundary layer. But of course we have nothing like that here. And the tufts don't tell you anything about boundary layer. As a matter of fact, one of the interesting things about these tufts is I chose them so that the diameter of the tuft is approximately the same as the boundary layer thickness. So everything that's occurring in the boundary layer is smaller than the diameter of the yarn that's on here. So can't see it, so we use the Reynolds number to tell us something about what's going on with that boundary layer, laminar, turbulent, and so forth. Now, when we're in this no man's land of Reynolds numbers from 100,000 to 500,000, what do? Most aircraft say, oh, I don't want to operate there. I don't know anything about what goes on there. I just know it's a lot of trouble. So they either design the aircraft so that it has Reynolds numbers that are higher than the problem area, or they do something mechanically to create a turbulent boundary layer, and usually that's vortex generators. Now, we did try vortex generators here early on and placed them just in front of where the elevon hinge line is, and didn't help at all. We thought we'd be able to energize the flow before it has to go around the corner when the elevon's deflected down, and it didn't work. So I thought, well, maybe it's not a Reynolds number problem, and this wing is essentially the same as my first wing. I don't see why I have a problem. So, do I really believe it's a Reynolds number problem? Yes, I do. And you might be asking, why? Why do I think it's a Reynolds number problem? Because I've seen flow conditions exist on the wing which are indicative of a laminar separation bubble. And why don't we take a short break here? I will run some previous videos that show that effect, show the things that I've seen. The elevon's deflected down, we get separated flow, it goes out to the tip, but even when the elevon's up, there are situations where the flow begins to separate, and we see these tufts doing all kinds of weird things. There's going on, you might see some circular flow like this, like these guys are pointed out, and these guys are pointed in, so there's some kind of circulation going around here. Chaos, aerodynamic chaos. So that's indicative, and we'll go take a look at that.
Here we're looking at the left wing as I'm preparing for the first flight that I made at Marina Beach. Inboard we see the flap, and you can ignore the flow in that area. Outboard you see the elevon deflected down about anywhere from 20 to 30 degrees, and you want to watch the tufts there. Right now it's down, and the tufts are somewhat attached in the first portion of the elevon and then pointing outboard. So there's separated flow on half the elevon there. The elevon's back up and the flow's reattached, and that flow looks fairly decent. There's some tufts further forward on the wing. You probably ignore those. There's a couple of them that are stuck on the tape and so forth, so they can be reliably ignored. So I'm trying to get the wing stabilized and level here before I take off. And shortly here I'll start to move forward a little bit. Let's see when that comes up. But as long as the elevon is straight back like that, no angle of attack, the flow looks very good. And here I'm moving. Elevon comes down a little so I can pick up that wing. That wing had started to drop, and there we see the flow build up spanwise on the aft portion of the elevon. So it is clearly separated, and that's a bit of a problem because that generates a lot of extra drag on that side and causes me to want to yaw to the left, which is the last thing I need at this point. So I get the wing moving a little bit, and as I get some lift developing, I should be able to bring that elevon back up. Right now I'm feeding in down elevon because the way that we have me strapped into the glider, the way that I'm picking it up, it's a little tail heavy, and I'm using elevon to get the nose back down, which is probably a bad plan for this particular scenario. Now the elevon's going to go up here as I attempt to rotate for takeoff. You'll see that shortly here. There, I'm up. And then you see a lot of left stick. This is left aileron and up elevator as I initiate my turn so I don't fly into the ocean. I get that turn initiated, then I back off the elevon, or the aileron I should say, so I don't overbank and put the wingtip in the sand. I'm only about 8-9 feet off the ground here. There's a little more aileron so I can get the turn to continue. Flow looks good with up elevon. My original wing, if I had that much elevon up, it would start some spanwise flow, but the winglet sitting there helps stop that from happening. Flow on the forward portion of the wing looks good, so we're doing fine. I get the wingtip pretty close to the ground here, then I back off that aileron. I really don't want to go in the ocean, so I'm banking as much as I can to get it around the corner so I don't head out over the water. And I'm struggling with the pitch right now. There's some stall occurring there, and I hit down elevator to stop that stall. And I don't know if that stall is probably caused by premature separation on the elevon. Whether it's a laminar separation bubble or not, I don't know, but that was the start of a stall. And as I come around here, I attempt to pull in some up elevator to slow it up, but at this point I'm sitting too far forward. There's another stall starting there, and I do think that the stalls are predicated, I don't know, is that the right word? The stalls are started by the flow separating off the elevon. If we keep the flow attached to the elevon, I shouldn't have a problem with those early stalls like that. A little more up elevator as I attempt to land, and then the landing's hot, and this is where I tore all of the down tubes off the pilot's cage. I think you'll see me fly into frame here in a second. Nope, we didn't get to see that. This is the right wing, same flight, and you see a lot of spanwise flow on that down elevon. A lot of spanwise flow on the flap. It's experiencing the same type of conditions as that low speed, low Reynolds number flow tries to go around the corner. It can't. Runs into the adverse pressure gradient and just goes out spanwise. Not a great thing on the flap, but not something that would cause me any undue problems because the same thing's happening on the other side. So the extra drag that it's creating is symmetrical. However, that down elevon, separated flow on half of it or more, and it's creating a lot of extra drag. And then as I pull in up elevator to take off, we'll see the flow reattach. Everything's fine. There's the rotation, and there's the start of a stall there. That might be a laminar separation bubble. I don't know. The elevon's back down. Now we have a bunch of spanwise flow. Not good. Not helping the situation any. And elevon comes back up. I'm top-siding the turn a little bit so I don't overbank. There's the start of a stall. We got a bunch of really messy flow there. Not helpful. And then right about here, I got everything neutralized, flows attached, and this is where I really started to scoot along. There's the start of another stall. Once I get all the flow attached, and of course I have no idea I'm doing this, but once I get into a stabilized condition and the dune drops off a little, boy, the thing just really got up and went. It's got great performance when the flow is actually attached to the wing. And here we see some spanwise flow inboard on a portion in front of the flap. That's not a good thing. That causes problems. Here I'm topsiding the stick to prevent overbanking. The same flight, so this is where the other wingtip's very close to the sand. There we get neutralized out. And a little bit of down elevon there to keep me in the turn. Don't want to go in the water. And there's the start of another stall with the elevon up. Just really messy, nasty flow on the whole thing. So I'm probably only flying maybe 25 miles an hour here, maybe 28. Reynolds number is probably around 600,000 out on that elevon. And it's just stalls coming and going as I try to get it through the turn. Because I'm trying to hold minimum speed. I'm trying to keep from careening into the sand at 40 miles an hour or something like that. That'd be bad. And I just did not have enough elevator to get the nose back up in time.
Okay, welcome back. We took a look at some of that crazy flow and saw stuff that's indicative of laminar separation bubbles. And hopefully, if I remember, I'll have put up some pictures of theory of laminar separation bubbles, where they occur, because they can occur up front or further back and so forth. And they occur in different places at different Reynolds numbers. But they are very difficult to predict, and they have a relatively random nature. So, how come none of the fixes that we've tried have worked, And we eventually got pushed down to, okay, the problem occurs, we had to concede that the problem occurs when I deflect the elevon down more than 15 degrees. Flow separates, I lose control of the aircraft. And it's a double whammy, it's really bad. As the elevon goes down, the flow begins to separate, and of course the down elevon is lifting the wing, so if I want to roll right, the left elevon is down, and that creates more lift on that wing and begins to lift the wing. But if the flow starts to separate, you lose lift on that wing. So does the pilot do? Oh, I'm not rolling fast enough. He doesn't stop to think, oh, the flow is separating out on the elevon. Oh, okay, no. He's like, I'm not rolling fast enough, not rolling. So you put in more right stick. Put the elevon even further down. Oh, and the flow separates even more, the problem gets worse. And then, you really get separated flow, you get a massive amount of drag, you get adverse yaw, and you start to actually point the nose opposite of the way that you want to go. So what do? You put in more aileron. It just makes the problem even worse. It's a divergent control system. Really bad. Happens very fast. So all of a sudden the nose is yawed off the wrong way. I'm no longer rolled. I'm flat. It's terrible. At best, you panic and you let go of the stick, and then the glider goes back to flying itself, and you just go straight ahead. So, not a good situation. Very difficult to deal with as a pilot. And that's why you end up being a spectator. You just sit there and watch it happen. And you go, whatever I'm doing is not working. Bad. Okay, so one way to cure problems is to avoid them. You don't really fix the problem, you just don't cause it to happen. And we went through a bunch of stuff, we figured, at this point, the best thing I can do is just don't deflect the elevon more than 15 degrees. So I actually set up some differential in the elevons, and I wanted to give myself a little bit margin, so I said, okay, I'll take it to 20 degrees, and that'll be enough. And I'm going to need more control surface area, because if I can't deflect my elevon down 20, 25 degrees, if I can only do 15, well then I'm limited in the amount of control authority I can generate. So I make up for that lack of control authority with bigger elevons. And that's where we went. That's where it ended up going. I did a series of tests where I tacked a 9-inch extension onto the trailing edge and used this as the elevon. That's when this portion of the wingtip was all rigid, not hinged, one piece, and I added Elevon on back here. And we went and tested that. And we're going to take a little break here. We're going to go look at that, and I'll talk through that video, and I will compare it to with and without this extension, and we'll see the different flow conditions.
Here we can clearly see that I've tacked that added Elevon onto the tip panel. It's very clear to see. The first thing that we really note is, wow, look at the flow conditions. They look so much better. It's not any windier or flying any faster here. I'm standing still on the ground doing ground handling. So we're probably doing 15, 17 miles an hour. Inboard and outboard, the flow looks great. Elevons go up, elevons go down. Everything's pretty well behaved. My buddy Dave had to come out and unstick some of the tufts. So there's some up elevon applied. Here I come in. There's some down. Flow still attached. The tip starts to go a little bit spooky right there. There's the tip of the extension is getting some reversed flow, and that's because it's truncated there. That's the end of it. There's a vortex curling up around that thing, causing the tufts to go awry. But overall, when my buddy Peter looked at these pictures, he looked at it and said, "Wow, the flow looks much better, Ron." I go, "Yeah, it's great now." And I have double the roll rate. I added this chunk of Elevon. It's not huge, but it is significant. And I have really nice roll rate now. And it's very easy to handle the glider on the ground. And I'm not getting massive amounts of flow separation. So at this point, I figure good to go. We're just going to cut the Elevon out of the wingtip. And we'll continue the reverse taper in the same rate as I had it on the inboard Elevon. And this thing's going to be peachy. It's going to fly great. So that's what I proceeded to do. And darned if it just didn't work out like I planned. Let's watch this till it runs to the end. I think you'll see me trot forward here a little bit, maybe. There's a lot of down Elevon there, and the inboard 2/3 of that Elevon addition, the flow's just fine. That's deflected down way more than 15 degrees, and the flow's attached. So at this point, I think, problem solved. Everything looks really good over the wing. So it should be quite manageable. And I did a series of little taxi test ground runs here where I'm pitching the aircraft up and down, taking it up to stall and back down again. I had very precise pitch control over it. Never had any sense of losing control. I didn't do any roll reversals, but if there was separated flow and oddball drag, I would have noticed it here.
It's very clear that with the Elevons being larger, I had much more roll authority. In fact, I doubled the roll rate of the aircraft with those extended Elevons. And as my buddy Peter pointed out, first thing he saw in those pictures was, "Hey, wow, the flow looks a lot better. Those tufts are straight." Even inboard, they're straight. Where at one time, they were all over the place. And the testing being done at Marina Beach with these extended Elevons, relatively low speed. It's down around 15 miles an hour, maybe tops 20. Smack dab at stall speed. And very low Reynolds number. Still, about 410,000 here out at the tip. But here where the extension is, the Reynolds number is higher because the characteristic length is longer, right? Well, I didn't think too much about it at that point. It's true, but I didn't put much, it just hardly crossed my mind. They're like, oh, bigger Elevons, more control, better, don't need to deflect as far, good to go. So went back, removed the temporary Elevon extensions, and cut out the Elevon on the wingtips. A lot of work, cut up good wingtip panels, and give me a chance to extend the reverse taper of the Elevon, which I like. The drawback was I now have control surface out of my wingtip where my intention was to never have control surface to help avoid the stall spin problem. But I thought, you know, if the aircraft's not flyable, yes, I have solved the stall spin problem because you can't stall and spin if you can't fly. In that case, you're hangar clean, and the problem is both solved and not solved at the same time. a paradox. Okay, so bite the bullet, cut out the elevons, and go, I've tested them, I know they're very effective, and I'm not going to be needing these big controlled deflections anymore. And everything should be peachy. And the flow looks great, nice and straight, all attached. So, get out there with these elevons, no extensions, and go to test it the other day. And darned if we don't still have problems with the flow out here was good at the tip. Where I put this hinge line up here where the energy of the flow is highest because it's the highest speed flow, most energized boundary layers up here. Put the hinge here. Yeah, in this area out here, the flow is getting around the corner and going down the elbow, stays attached. Inboard, not so good. In fact, same problem. Flow begins to separate. I put in more elevon, separates more, yaws the wrong way. Problem. Okay, especially a problem when it yaws the wrong way. Just the natural reaction is to put in more elevon.
So here we are, a couple of months later. I have, as you can see, I've cut the elevon out of the wingtip panel, and I just followed the same hinge line as the inboard elevon, and that took the hinge line very close to the spar. And I wanted to do that on purpose because if you watched the earlier videos, you know that I did some tests that showed if you do this, you're picking up the flow that has more energy in it near the maximum thickness point, and the flow stays attached better to the elevon. And here we're seeing pretty good flow conditions. That one tuft that's pointing backwards, I think that's just hung up on a piece of tape. And I think everybody had very high expectations that this was going to work great. And we're at the beach again, and I'm going to do some little ground runs here. But first, I'm just doing ground handling in place here. And it was fairly easy to ground handle. However, that big chunk of elevon that I added out on the wingtip panel weighs quite a bit in terms of everything else on the wing. And it about doubled the control forces on the stick. So my plan at the time was when I get home, I'll just put counterbalance weights on it. And there we see some of that classic second half of the elevon flow separated on the inboard portion, and the tufts go out 90 degrees. Now at the tip of that elevon, we see that the tufts are still pretty well behaved, and that's because I'm using the higher energy flow near the spar and asking that to go around the corner instead of the lower energy stuff. And as you get inboard, that hinge line is further away from the maximum thickness point of the airfoil, and the flow is already into the adverse pressure gradient, and then we're asking it to turn a corner. And this was a key part of the clue that we had as to what was going on, in that as you get further back into that adverse pressure gradient and the flow has been depleted in terms of energy, then you're ripe for separating the flow and having the flow just go straight out to the wingtip. So the tip of the elevon is behaving nice, but inboard is not. And you'll see that unlike when I had the elevon tacked onto the trailing edge, now the inboard elevon is having problems again, just like it did in the past. We're getting span-wise separation and span-wise flow there, which is fascinating to think about. But that's the effect of a potential flow field. You change flow in one area, and if that area is allowed to go span-wise, well, it's just going to drag the other flow with it. We have incompressible flow. We can't have a vacuum in there. Can't compress it, can't have a vacuum. So the other flow just goes to fill that vacuum, and you're dragging the flow off the wing span-wise. So if the tip is messed up, you're going to mess up inboard, and you're going to have some nasty time. You're going to have a nasty time trying to control the aircraft. So this is not what was expected. We saw that really nice flow when I had the temporary elevon tacked onto the trailing edge, but now that it's cut out of the wingtip panel, we're not getting that nice flow anymore. Now it's messed up again, and that was quite perplexing. And in a little bit here, I think I do a little ground run, and with these ground runs, I tried doing some rolls. I would roll it to the right and see how much control I had over it, and rapidly discovered that I get this massive adverse yaw when that flow goes spanwise and separates, and to the point where the glider's not you can't handle it on the ground. It was awful. It's like, wow, how can this one change? So I took off this funky, cheap, junky foam core addition onto the trailing edge and make a proper elevon out of it, and now it doesn't work. The other one, just that flat sheet of foam core, worked very good and fixed up the flow inboard also. And then I go do this nice hinge line and everything's screwed up again. It's really quite frustrating and very perplexing. So here I'm doing a little run, and I'm fiddling around with a pitch here. And, oh, there you can see me struggling. And there at the end of that run, you saw where the wing came back and it started yawing hard to the left, even though I'm commanding a right turn. I got that down elevon in there to command the right turn, but the wing is yawed left, and very unpleasant, not what we want.
And another factor that was involved here is I wanted a wing with superior performance. We were aiming for an L over D of 30 to 1 or better. Usually in designing gliders, you can get a higher L over D. Well, consistently, you can get a higher L over D by increasing your aspect ratio. Now, the aspect ratio is simply the span squared, tip to tip, divided by the wing area. So there's two ways to increase your aspect ratio. Reduce the wing area, so skinny wing, or increase the span. Now, on foot-launched aircraft, we need a stall speed down around 20 miles an hour. So just simply decreasing the wing area, bad plan. Very rapidly, you end up, to get to the aspect ratios we want, you end up with not enough wing area to actually take off. Your wing loading is too high. Your stall speed is up around 30, 35 miles an hour. You can't run to get it off the ground. Make a good ultralight sailplane that you tow, but you ain't going to run it off the ground. Okay, so you increase the span. Okay, and at that time I thought, oh, it'd be cool to be a foot-launched standard class sailplane. Let's make it 15 meters. Cool. And that's kind of where things were headed anyway. So I knew that at a 15-meter span should be pretty easy to get in the range of 30 to 1 L over D, even with standard NACA airfoils. And I thought, I will just start with 15-meter span and meet the 43% of the semi-span requirement for the mean aerodynamic chord, and make sure that I have enough wing area to get my base wing loading down to 2 pounds per square foot, which is going to get me close to that elusive 20 mile per hour stall speed at 300 pounds gross weight, gross takeoff weight. And then I'll do what the Swift did. I'll add a little flap and have that flap deployed for takeoff. The Atos uses one. I think the Ecstasy has one. We're getting in the areas of wing loadings where you need a little bit of flap to generate some more lift so that you can foot launch. And that would get me, it'll get my stall speed down to, as it turned out, about 22 miles an hour, 23 miles an hour. And with a little bit of headwind, I'll be able to get the thing off the ground. And we've seen that I've actually been able to do that. But in the whole process, so you end up with an aspect ratio that's somewhere in the range of 16 to 19. As a thumb rule of thumb, you can take your aspect ratio and double it and add a little bit more, and that's pretty close to the L over D that you'll get. And that's pretty much what works out for this. I have an aspect ratio of about 16, 17, something like that. You run it in X-Flow, and in theory it gets an L over D of 35, but in reality it's really going to be more like somewhere around 29, 30. And that's only after I get the cockpit area have a fairing around it. You got to fair that in order to hit that L over D. So there we go, 15 meters of span, I got 150 square feet of area, so I got 2 pounds per square foot wing loading at my 300 pound gross weight, and there we go. And then I spend the next 3 years building the darn thing. without ever stopping to really double check, triple check, and make sure that everything's still kosher. And at that point, I got a wingtip chord of 24 inches and a Reynolds number at stall of about 410,000, and really never took note of that. I might have looked at it and seen it in my spreadsheet and went, oh, okay. And not stopping to think, uh-oh, I'm below 500, and go research that a little, where everybody's screaming, hey, you go below 500, you're going to have a problem with laminar separation bubbles. Yeah. And, you know, it really isn't on the size range of my original wing. My original wing was about 34, 35 inches out at the tip. At the very, very curved over tip, yeah, less, but at the last rib, right around 34 inches. And that was more like 500,000. Had a slightly lower stall speed, down around 18, 19 miles an hour, but still getting pretty close to right around the 500,000 range, in and out of it. But enough to make a difference. So really not like my original design, and so pretty small tip, low Reynolds number. I go, how much of a problem could that actually be between 500 and 400,000? Is this really a problem? There's other hang gliders out there operating, and the Reynolds number diagram we looked at, well, hang gliders operate in that range all the time. How come they don't have a problem? They don't have elevons. They're not deflecting an elevon down. They're not experiencing the separated flow. In fact, on hang gliders, it's wing warping. And even more special about hang gliders, it's wing warping up only. What we do with a standard flex wing hang glider is we allow the wing to shift, and we allow one side to billow up more than the other. It's not that we tighten one side down. Well, we do a little bit, but mostly we allow the other side to billow up. It's essentially up and around only, like this. And that's how we turn flex wings. Very efficient. No hinge lines, no other problems to deal with other than it's limited in its very nature. It's inefficient in terms of drag at high speeds because the wing stretches and moves around on you and doesn't keep the shape that you want for best performance. But all aircraft are a trade-off, and for something that's foot-launched and highly transportable, it's the peaches. It's the best way you can possibly go. Okay. Interesting. So, hang gliders, wing warping, no problem. Plenty of control, no flow separation, no weird behavior. Okay. Yeah, but let's go back to my first wing. First wing, okay, a little higher Reynolds number, but I didn't have any of this weird spanwise flow when the elevons were down. Didn't have it. Up, yes, and I've talked about that in previous videos about spanwise flow and the work that I've done to prevent that by moving the winglet inboard and doing other things. But that sucker had really nice controls. My first glider, you could fly it with one finger like this, really light, beautifully balanced. And it would roll when you wanted it to roll, and the pitch was not overly done. It was sweet. Well, these control surfaces are much larger, and they're not doing the job because the flow's separating. And I went around and around and around about that. It's like, what the heck changed? Well, I had long strip elevons on my original wing. They were about 6 inches wide. They were about this size, maybe 8 inches wide. And they were stuck on the trailing edge. Why were they stuck on the trailing edge? So I had my regular airfoil, and then when we would deploy the wing, you know, it's kind of like a Millennium. It had D-tubes and fabric and ribs that folded up, or like an Atos. And then you get the ribs deployed and attach the elevon, put in 3 pins, and you're good to go. And the receiver is the end of the ribs, right? The ribs had a little eye bolt in them, and you run a pin in there and attach your elevon. And the elevon was essentially a flat plate, so only 3/4 of an inch thick at the front, almost nothing at the back. So, for all intents compared to the airfoil, a flat plate tacked on to the trailing edge of the airfoil. Worked great. So, I think, you know what? The Millennium's the same. Why is it the same? Oh, well, when you stop and think about the whole problem, okay, I want rigid wing performance, but I want it in a package that I can fold up. So that just drives you to D-tube, folding ribs, fabric, take it apart, fold the ribs, roll up the fabric, go home. Right. What do you do with the rigid elevons? Well, you can hinge them so they flop forward like this, but if they're fairly wide, how do you roll them up in the fabric? How do you package them? You take them off. It's one way to do it. I believe that the Millennium, that they're attached with the fabric, and the fabric serves as the hinge also, but it kind of folds over with the fabric, and you fold it up and you lay it on top of the D-tube. The Swift, real rigid wing, like this one, it folds them all the way over flat. So you essentially have a package like this that you slide in your trailer or box on top of your car. So the Millennium's got the standard answer that anybody would be driven to is to, you want it to be transportable, just tack an elevon on the trailing edge. Because if you got a fabric wing and ribs that fold up, how are you going to have a hinge line like this? Mechanically, a nightmare, and probably pretty damn heavy. This is probably a more efficient, aerodynamically efficient configuration is to actually bend the airfoil, change the camber line, and efficiently generate more lift so you can roll. This is a compromise in between. This isn't going to be aerodynamically as efficient, but mechanically much simpler and lighter. And because we're in a hurry to build these things and we want to get out to the field and try them, it's like down and dirty, tack it on the trailing edge. So Millennium did that. Who else did that? Oh, pretty close on the MkII wing. MkII wing had what a lot of people think are Yonkers flaps, but they're a little bit different than that. It was a separate control surface that was positioned down here very close to the wing. Yonkers flaps are usually down in here somewhere. You have a sizable gap like this, and they do this down here for aileron control. But the MkII wing was up in tight like this. It's 6 or 8 inches wide, and they were mostly designed, or they were designed to go up mostly like this, because their pitch stability is achieved with reflex of the flaps out at the tips, and normally they ride in a slightly up position like this to generate that reflex, and then to roll the aircraft they go up higher, and when they come, and there's a bigger gap as they do this, and some of the air is going through there, making them very efficient, and the flow stays attached because you have accelerated flow going between the wing and the Yonkers flap like this, and you get really great effective control that way. And then when they went in the down position, they would close that gap up like this for normal cruise. I don't know if they ever closed the gap all the way, but the issue with Yonkers flaps is that at high speed, they're draggy. They create a lot of drag, and you're not going to get really high performance with Yonkers flaps on your wing, especially up around 70, 80 miles an hour. Like 70 or 80 miles an hour, who flies that? That was one of the purposes of this aircraft. I wanted to be able to cruise it at sailplane-like speeds, up around 70 miles an hour, and design the structure and everything else to be able to do that. Now, when they did the Swift, that was back in the 80s, and hang gliders were flying around at 25, 30 miles an hour. You know, if you went really fast, you're going 40. So, the Swift can go a heck of a lot faster than 40. 45, 50, 55, 60. Oh man, you're screaming. But the Swift was never designed to do 70 or 80 miles an hour. Nor was the Millennium. Nor was my original wing. My original wing would do it. You put the nose down, that thing was so slippery, go really fast, you go right over red line. But red line was down around 75 miles an hour. This thing has 100 mile an hour red line on it, I hope. So, different animals. Okay, so the Millennium has trailing edge flap elevons. The MkII wing, something quite similar, that worked good. Millennium flies fine. Now what about the Swift? You might say, well, the Swift, all rigid wing. Elevons aren't tacked onto the trailing edge. They're cut out of the wing. just like a regular aircraft. And I go, yeah, that's true. So I have to go look at the Swift and say, what's up with the Swift? That works. I've gone out and tufted the Swift. I know that it'll do 17, maybe a little bit more degrees of down elevation deflection before any separation begins to occur. I also know that it has a turbulent boundary layer across the entire chord of the elevation. Like, wow, Swift gets it to work. How come it doesn't work for me? Well, they are different airfoils. The Swift uses a low Reynolds number airfoil. Why? Because they fly at a low Reynolds number, just like all other hang gliders. And they can get a high L over D. They're trying to achieve the highest L over D possible by having an airfoil that performed well at low Reynolds number. Yippee! Here's what that type of airfoil looks like, and I'll put it up here somewhere. And I'll talk to it here a little bit. You'll notice that the maximum thickness point is further aft. It's about at the 40% of chord instead of 25 or 30%. And it dips down rapidly behind the maximum thickness point and then goes out to a fairly thin area in the aft portion of the airfoil. And that's where the difference lies. The pressure recovery after the maximum thickness point of the airfoil is drastically different for low Reynolds number airfoils than it is for quote-unquote standard airfoils like I put on here, a MkII airfoil. And I will put up those two pressure recoveries for you here. And you'll see that there's essentially a linear slope for this airfoil from the maximum thickness point all the way back to the trailing edge where the pressure is being recovered. And we call that the adverse pressure gradient because it's downhill. But you got to understand that these plots are flipped over. Minus pressure is up, positive pressure is down. So we're going from low pressure to higher pressure in a linear fashion. That's an adverse pressure gradient. And I've talked before about how the flow coming off of the leading edge of the wing has got to penetrate all of that adverse pressure gradient. So it's going fast up here, but the pressure is low, and it's got to push into this pressure gradient as the pressure goes up. Pressure's going higher, 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 higher as it comes back to the trailing edge. And it takes energy to push into that adverse pressure gradient. And if you don't have enough energy in the boundary layer, you'll never get there, and you'll separate because of the Reynolds number issues. Well, the Reynolds number tells you when you're going to have an issue. So if you don't have enough energy in the boundary layer, if there's not enough inertia, the viscous forces and the pressure gradient are going to stop you from moving forward, and you're going to look for somewhere to go, and you're going to go over here, and you're going to go over there, and you're going to try to get back to the trailing edge one way or another, but I got all of this higher pressure here in front of me stopping me from going, and I don't have enough energy to get there. So, maybe it'd be better to go over this way. There's still low pressure over here. I'd much rather go either one of these directions because it's lower pressure than trying to beat into this higher pressure gradient. I don't have the energy to do it. And then you get a laminar separation bubble. So we deal with that by turbulating. We can deal with that by turbulating the boundary layer, putting trip strips on here to add energy to the boundary layer. This airfoil at 400,000, you should be able to put a trip strip on it up here and trip the flow and create turbulent boundary layer and keep it attached. Well, I've done that. I've done that in the most recent testing yesterday. And this, in fact, I tested 5 different types of trip strips all up here at the 1/3 chord position where the velocity is the highest. And I tested just a little ramp here, a 3/16 of an inch tall step like this. Okay. I tested, what is this? 3/16, not 3/16, this is about 1/8 of an inch up here, but much wider. I tested a triangle stuck on here, and I tested this big ugly thing straight up like this. And man, if you can't create turbulence with a bunch of holes, how else can you do it? Well, first of all, This one was a really great spoiler and nothing else. All it did was completely ruin the flow on the wing, and if you needed to come down fast, this would be great for that. So that's out. The most efficient spoiler I've ever seen in the whole world is this silly little triangle. You put a sharp point sticking up on a wing like this in a triangular shape. In other words, the flow would go up, hit this edge, and straight off the wing. It's like, wow, this little tiny triangle, you could spoil the rest of the flow on the wing. You want to have a great spoiler to get down into a tight field in a tight spot, triangle, great way to do it. I discovered that yesterday. I was shocked. I've seen a lot of different spoilers, turbulators, what have you. I've never tried this before, but boy, if you want a really good spoiler, this is the way to go. But we're not looking for a spoiler. We're looking for turbulators. That's out. Okay. This guy. Oh, you drop off the ledge here on the back side, or the flow tries to go straight, and you get a little tiny vortex that forms in here where the flow is detached. And the vortex can scoop up energy out of the flow and carry it into the boundary layer, and that's all theory, and that didn't work for crap either. Okay. It's just another spoiler. Okay, but you notice the way that I have my finger going. It's going this way. The flow's going this way. And you get that little vortex like this. Model airplanes use something similar. They'll put a wire on two posts above the airfoil, and you get a von Karman vortex streak coming off the wire, and that pulls energy out of the free stream and takes it down to the boundary layer. It works great down at the lower Reynolds numbers, but not in this case. This thing was even worse. Did nothing. You'd hardly know it was on the wing at these stall speeds. And I was operating yesterday 15 to 20 mile an hour wind blowing, so right close to stall speed. So that's no good either. So a lot of junk. And then I had these other four over here that I was going to test, but by the time I did those and realized none of those were working, those were all crap too. So now we're down to this guy. What we have here is a set of standard, semi-standard vortex generators. Little triangles that are angled to the flow like this. You put those right up there like that. And as the flow comes in this way, this is like a little wing mounted at an angle to the flow. So it's stalled. This is like a wing that is stalled. Now these are at 45 degrees, so it's in a really deep stall. And what happens is you get flow separating behind this wall. So as the flow comes in this way, it doesn't turn and stay attached. It tries to turn, separates, and rolls into a vortex. And that's the trick to these. It rolls into a vortex this way in the direction that the flow is already going. That's a good thing. And you get one off of this side. Now, as I've come to learn, last night I went and read up on the proper angle of these and spacing and height and everything else, and that's a bit of a black art too. It's getting a little better defined in recent years, but 45 is way too steep. Should be more like 15 degrees, 18 degrees. 15 seems to be about an optimum. They should be spaced a lot closer together. Not clear that they need to be this tall, but for the testing I was doing yesterday, this is good enough. First shot. Put it on here and discovered that the flow on the Elevon was a little bit better. So I found that there is a spot where I can turbulate the flow, make it a little bit better on the Elevon, and that got me from about 15 degrees of deflection on the Elevon before separation up to about 17 and a half degrees. So I gained 2.5 degrees of deflection before the flow really started to separate back here. Well, that's nice, but it's not as much as I'm looking for. I'm looking for 20 plus degrees of deflection. Now, those are not optimum, those vortex generators. They're well off of optimum. And if I had them full length in front of the control surface, and they were spaced properly, right height, right angles, maybe they'd work considerably better, and I'd get another degree of deflection or so. But, as everybody would immediately say, well, when you want to go fast, this is as bad as the Yonkers flaps, right? You're going fast, and you got vortices coming off of here, and you got nothing but added drag. Now, a turbulent boundary layer that's attached will be lower drag than a laminar separation bubble. But at higher speeds, I don't have laminar separation bubble problem anymore because my Reynolds number is now high enough to be outside of the region of that problem. So I only need these when I'm flying near stall speed. So if I have vortex generators on here, to really get good performance out of my wing, they're going to need to be retractable. which I could do. I could interconnect it with a flap. So when the flap's down, they're up. They're generating little vortices, keeping the flow attached, making that turbulent boundary layer. And then as I pull the flap up, these would retract down inside the wing. And the mechanism could be made lightweight enough, simple enough, where it's just a spring-loaded pull string type situation, and they go up, they go down. And you'd put them back out for landing. Eminently doable, but not without making very significant modifications to my wing. And then there's another problem. Nominally, it looks like the optimum location for these vortex generators is not here at the peak of the airfoil, which happens to be where the spar is, not back here behind the spar, where these would be really easy to mount because I could take the fabric off, put a tray in here, got little pop-up vortex generators, but more up here on the leading edge. And the way these structures are built, right to the nub in terms of strength to weight ratio, if I cut a bunch of slots in that D-tube to allow these guys to pop up, I'm going to have to do a bunch of reinforcements. I have to carry the loads around those slots, and it's going to get heavy and complicated in a hurry. Plus, in order to make that modification, I have to build 2 new wingtips. Well, gosh, it's a good thing I hadn't finished the other wingtips, because I might need to get inside the D-tubes and cut slots and reinforce and build something like this into the D-tube. So let's go back to what I was discussing before about the trip strip and keeping the flow attached on the elevons and where the problem really lies. So we have this bugaboo over, it appears that, and I'll put pictures up here, the Impact hang glider, the Millennium, and the Mitchell wing, and my original wing all have elevons tacked on the trailing edge, and they all work. You have the Swift, which has the elevon cut out of the wing. It works too. Super design, flies fantastic. Plenty of controllability on that. Okay. This one, elevon cut out of the wing, doesn't work. Massive problems with flow separation. My Reynolds number, 410,000 out here at the tip. So I call up my buddy Daryl near San Francisco. He owns a Swift, and I says, Daryl, do me a favor. I know it's a pain in the butt, but go out, get your Swift down, measure the root and tip cord for me. And Daryl's a great guy. He did that for me. And he comes back, gives me both numbers. The root number is a little confusing because of the weird shaped flap, but I was mostly interested in the tip cord. Comes back 36 3/4 inches. Well, there you go. That's pretty close to my original wing, 35 inches. And gee, what's the Millennium? So I go back and I look. I don't have hard numbers on the Millennium, but I go back and look at it, and I know it's basic parameters, and the tip cord has to be pretty darn close to 36 inches, right thereabouts. Might be a little bit more, a little bit less, but right around there. Okay, what's the Impact? What's the Mitchell wing? So you go back. I go back and look at these pictures, and I do some calculations with numbers that are available. The Impact, right at about 36 inches, and the Mitchell wing, maybe a little bit more than 36 inches by the time you put that Yonkers flap on there. Oh, is that the magic number? 36 inches? And I thought, no, the magic number is 500,000 on the Reynolds number. That's the magic number. So work it backwards the other way. At our standard stall speeds that we need for a foot-launchable aircraft, 20 miles an hour, just in round numbers, maybe a mile an hour less or more, but right about 20. At 20 miles an hour, how much cord do you need to get a Reynolds number of 500,000? And the correct answer at sea level is 32 inches. This is fun part. When I tacked this on to the trailing edge of my wing, just to see if the added elevon would give enough control surface, and I went and tested it, and all the flow looked lovely, and I had plenty of control and all that. Then the cord was 33 inches. This is a 9-inch extension. Wow. I needed 32, had 33. Is that right? 24 plus 9, yeah, 33 inches. So I'm 1 inch more than the minimum I need. So I'm a skosh over 500,000 on the Reynolds number with this tacked on the trailing edge. Wow! Who knew? And you go, oh, you must, genius move. You added 9 inches to the trailing edge. Why did you add 9 inches? It must have had something to do with how much elevon area you needed. I'll burst your bubble. No, it had nothing to do with anything reasonable like that or logical. No. It's how many pieces of foam core strip I could get cut out of a sheet and get an even number of pieces and no wastage. So I accidentally end up at a usable answer by being a penny pincher and not wanting to waste any foam core and had to have an even number of sheets. Otherwise, I might have made it a little wider, and we'd never know. But that's how these things happen sometimes. You make design decisions based on something that has nothing to do with aerodynamics, and you stumble into the right answer. So it looks like right now that the better way to design a foot-launch flying wing, rather than saying I want to have this much spin, I want to have this much wing area, is to say, okay, I know it's going to weigh about this much, and we can just say 300 pounds, because your airframe is going to weigh 100 in round numbers, and your heavier pilots are going to weigh 200 pounds like me. So 300 pounds. And I need a certain amount of lift to get my wing off the ground at a reasonable speed, like 20 miles an hour. And as you finagle the numbers and you get the aspect ratio higher, right, as you stretch the span out and hold that area at 150 square feet, and I'm getting aspect ratio, well, the tip gets really small. That's how you get down to 24 inches. But it looks like the right way to do it is to say, I got to have a tip chord of 32 inches minimum. Because at that stall speed, I want to have 500,000 Reynolds number out here at the tip so that my flow stays attached. Interesting way to do a design. Nowhere in all of my design efforts or training have I ever been taught to start with a tip chord and work from there. But that's how these things should be designed. You start off by saying, I need a minimum tip chord of 32 inches, and go from there. And as it turns out, at 150 square feet and 15 meters of span, 50 feet, and if you want 150 square feet, well, darned if that isn't 36 inches, 3 feet. And you might as well just have a constant chord flying wing. There can be advantages to tapering it in terms of aerodynamic performance, but you can adjust for that with twist in the wing. And there certainly are tremendous advantages to having a constant chord wing when it comes to building it. All the ribs are the same. I don't need two separate molds for D-tubes. I only need one mold, same D-tube both sides. And you might be saying, hey, what about the twist? What about the washout? But as you've seen with my D-tubes, before you put the shear web in, they're completely flexible like this. So you can just build constant chord and twist it this way for one wing and twist it the other way for the other wing and glue it down, and it'll stay that way, especially if it has a couple of nose ribs in it. So now we don't need to make as many molds. Well, there's some advantages to this concept of constant chord flying wing. And right now my current thinking is that might be the best answer overall in terms of balancing all of the parameters. I know it gets a little boring. Every single foot-launchable flying wing out there would be constant chord. They'd all look identical. But we're working in a design zone where there's very little room to make changes that increase performance without ruining something else entirely, and you end up with an unusable aircraft. It's quite an interesting situation and a challenging design. So as I've worked through this and thought about it some more, I thought, hey, what about the Atos? Now, it doesn't have elements, it has spoilers. In fact, their spoiler sits like right in here, like this. And they have a couple of them. I'll put up a picture of one. And spoilers work by, they come up like this and they spoil all of the lift back here. And that wing drops, goes down. okay? And they have dihedral in their wing. It looks a lot like my wing before I took the dihedral out. So this wing drops, and it creates a lot of drag from the separated flow. Separated flow, loss of lift, wing drops, yaws back, yaws in the proper direction, and then the dihedral effect takes over and rolls you into the turn even more. Very powerful control methodology and works fantastic. That's a very maneuverable hang glider. Absolutely rigid wing. There's no warping at all. Completely rigid. It's built a lot like my original wing, folding ribs and so forth. Fabric rolls up, but no elevons on it. And they're adamant. The folks at Air are adamant that elevons do not belong on a foot launch flying wing. And there's something to be said for that. But this is a world full of trade-offs. The problem with spoilers is they're always spoilers. Even when they're closed, they're spoiling the flow. Those spoilers sit on top of the fabric. They stick up about 3 millimeters. They're stitching in fabric in front of them. And they're only held down by aerodynamic forces. When they're deployed, when you move the A-frame, it pulls on a cable that pulls on a system, and a little lever comes up and pushes the spoiler up. But its aerodynamic forces push it back down. Well, aerodynamic forces vary, and you'll see at times, if you watch videos of Atos flying, you'll see that sometimes the spoilers on both sides are open. They're popping open. They're not held down really tight. And they really don't want a spring system holding them down either. That would be bad. And at high speeds, well, you got 3 millimeters sticking up on your airfoil back here, and it's wrecking the flow, in my mind, and it's creating drag. And it's like, well, and Patrick's like, well, how fast do you want to go? Patrick says, I can go 100 miles an hour in my VR. And I go, yeah, of course you can, but not efficiently, not as efficiently as possible. And he had to agree with that there's room for more efficiency there, better performance at high speed by eliminating messed up flow out here. And then as we talked through it, I says, but what's your tip cord? And he says, 25 inches. And I went, aha, mine's 24. You only have 1 inch more than I have. How come you don't have Reynolds number problems? I had to think about that one. Well, the spoiler sits right here where the laminar separation bubble would form, except it's a bump in the wing. And it's big, and it covers a large area. So probably, I would assume, we haven't tested it, I would assume what's happening is that little step in the big spoiler is tripping the flow, and they have a turbulent boundary layer, and it stays attached to the wing. Not that they planned it that way, but it just worked out peachy. So they don't have, even though they have the really small cord, they don't have the laminar separation bubble problem because they're tripping the flow with a very inefficient vortex generator. But it works great. Cuts into your performance, but it makes for a very flyable aircraft. So what do we have to do to get in the middle somewhere, right? To get the best of both worlds? I was talking to Pat Denovan at Fort Funston, and Pat says, so really, Raul, what you want is you want everything. And I go, yeah, precisely. I want everything. That's not easy to achieve. And Patrick kept going, no, you really got to put spoilers on it. I go, how am I going to do pitch control? You guys use weight shift for pitch control. You got A-frame, you got that nice weight shift thing. He goes, yeah. I says, damned if I can efficiently shift my weight as easily as you do in my big pilot's cage. And I says, and I can't put an A-frame on my wing because I got a little muscle problem and I can't pick up hang gliders with an A-frame anymore, so I got to have this pilot's cage and a harness and all that other stuff to pick it up. And other people would be in the same boat. We're getting older. And he agreed that weight shift was not a viable solution for my pitch control, and you need some kind of control surface to do the pitch control. No, we're back to elevons. No matter what you do, design corner, back in a loop. I can't have spoilers for roll control because I need something for pitch control, and by the time you put something on the wing that works, well, then you got ailerons too. They're called elevons. So here we are back at the solution again. We're back to this thing that I have tacked on here. And what this is this is a 9-inch extension on the back of the elevon here to bring my cord up to 33 inches and increase my Reynolds number up to 500,000. And darned if you don't know. You know, I'll take you over to the video now and I'll talk through that video. But you're going to see some pretty nice flow conditions here. It really is a problem solver. So let's go take a look at that.
Now, before I let this video roll, let me explain the weird angle you're looking at. Remember that the trailing edge of the wing is tapered down and the elevon attachment is a flat plate. So when the elevon attachment is aligned with the chord of the airfoil, it looks like there's a big kink in the wing. And there sort of is, but the camera angle and so forth makes it look much more drastic than it really is. So here we are rolling along, and right here I have about 0 degree angle of attack, getting set up here, and I'll bring it down to about 10 degrees down. Right there is about 10 degrees down. The wind is shifting, so we'll see the tufts move around, but they're staying attached. We're not seeing that 90-degree turn and blowing out to the wingtip or going backwards. So that's pretty well behaved flow. Then I go down to about 20 degrees. Here we are at 20 degrees down. No, this might have been about 15. 15 degrees elevon down, still attached, doing good. And I think here shortly I take it to 20. This was either 20 or, and then I go to 25. But here we have quite a bit of downward deflection on the elevon, and we still have nice attached flow. Everything's well behaved, other than the wind whipping back and forth. It was a gusty day. It's a pretty wind tunnel, but it's not consistently smooth. And in a moment here, you'll see me push it down until there's separation. That's down around 25 degrees right there, and we begin to see the separation. Tufts turning backwards and forth. That would happen on any aileron or elevon at that deflection angle. Never going to get too much more than about 20-25 degrees before you have a problem. So by extending the chord and boosting the Reynolds number, I'm keeping the flow attached for an additional 10 degrees of elevon deflection, which is a good thing.
And welcome back. So there's no sound on that, and unfortunately you can't hear me calling out the deflection angles of the elevon, but the maximum down deflection, as I mentioned in the video, I hope I mentioned it, is about 25 degrees. And the flow is staying attached up to about 20 degrees. Some cases 22, 21, depending on what the velocity of the wind was. And works like gangbusters. Now I can get a lot of deflection, the flow stays attached. We can go back and explain why when I just tacked on elevons on the rear and activated those up and down, the flow looked great on the wing and I had lots of control. And then when I removed this and cut out the elevons, it didn't work as good anymore. It worked a little bit, but doesn't work as good because the Reynolds number's back down to 410,000. So how do you save the design? Well, you need a bigger chord. And if I added 9 inches to the entire chord, well, now I'm up around 165 square feet of wing. And that's starting to get a little bit large if you want to go fast. The more wing area you have, the more energy it takes to go fly fast. It'll fly slow, much better, but you want to go fast. You want the least amount of wing area possible and go like hell. We're going to have a very interesting discussion about Reynolds number and what it really means in this case, and about elevons being tacked onto the trailing edge of the wing. And it's going to be a fascinating result. So keep watching.